The following video is an in-person test of the collision detection system. We have two sensors on each side of the head. When they detect a hand, the arm slows to a stop, and when no obstacles are detected, the arm smoothly accelerates and resumes its movement. This next section demonstrates situation tests. Because of COVID-19, we couldn't do any more in-person tests, so we designed virtual tests to check our collision system. Even though these tests are virtual, the interfaces for the Universal Robotics Simulator and the real arm are identical, making it easy to switch between the two. Each situation test has 3 steps. First, the arm moves to its starting position. Then, obstacles are placed in the simulation, and finally, the arm moves to its end position and may or may not stop. In the test just shown, the arm correctly stopped because a sensor near the head of the arm detected a nearby obstacle. In this next test, the arm starts very close to an obstacle. However, because the arm moves away from the obstacle and isn't in danger of colliding, the arm doesn't stop. This next test demonstrates how the arm stops before colliding with itself. This test doesn't need sensor data because it uses a simulated model of the arm. When the base and head of the arm get too close, the arm stops. Finally, here's a demo of the SafeVision Android app. There are 3 windows on screen. The left window is Polyscope, which is the UR arm simulator. The right window is our visualization program, and the phone shows the app. Before using the app to control the arm, users need to submit the correct IP address, port, and password. This brings the user to the control page. The top shows a visualization of the arm and its sensors. Right under that, there are 3 radio buttons that show the arm's operating mode. And under that, there are 6 sliders controlling the arm's joint angles. When users change joint angles, all 3 visualizations update together, which means that data is being passed correctly, from the app to our visualization through an HTTP server, and then to the arm through a TCP connection. When the user isn't moving a joint, the arm goes into stop mode, which can be seen both in the app and in the visualization. Even when the user controls the arm through the app, collision detection is still enabled, which means the arm stops before colliding with obstacles. This app, with a password-protected login, visualization, and collision detection, enables people to safely view and control the arm from remote locations.
Hello, we are SafeVision.
I'm Nathan Bornfriend.
I'm Rick Frank.
Hey, I'm Steven Landis.
And I'm Willie too.
For our Capstone project, we partnered with TrueVision Alcon, who helped surgeons during operation by providing 3D surgical visualization. This is captured with a robotic stereoscopic digital microscope that they've developed. The microscope is supported at the end of a universal robotics arm with a max payload of 5 kilograms. Here you can see the microscope is attached to the end of the arm. The arm has 6 degrees of freedom, which adds a lot of complexity to the movement. There are 3 operation modes, the first being free drive, where the user controls the arm by applying torque to the head of the arm. Second, remote control, where a user controls the arm through another device. And finally, automatic mode, where a set of pre-planned movements are automatically executed. The arm is unaware of surroundings, including doctors and equipment, and this may lead to accidental collision. Therefore, our goal is to prevent these collisions from happening. Here is an example of the arm being used in an operation room. The arm is being controlled through the free drive mode, and the screen portrays an image captured by the microscope. The doctor is focused on the screen and the patient, and therefore may not be 100% aware of the arm's surroundings, and this may lead to collision. Given this environment, our system must prevent object collision and safely stop the arm, which can move up to 0.8 meters per second. It must also move predictably, as the doctor must be in control of all movement in the operation room. All parts must follow medical guidelines, and it must weigh less than 1 kilogram, as the arm can support up to 5 kilograms, and the microscope weighs roughly 4 kilograms. Our proposed solution is to use distance sensors to detect objects in the direction of movement, as well as using a model of the arm to prevent self-collision. After the arm is stopped, we have to ensure safe conditions by checking for obstacles in the next direction of movement before resuming.
Here we have our overall system schematic for the project. It's divided into two main parts, the hardware and the software, with the hardware focused on the microcontroller getting the data from the optical distance sensor and sending it to our software system through UR, where the software is focused on the object detection, where it communicates to our universal robotic arm through real-time data exchange protocol to get the arm data and determine whether to stop the arm or not, depending on the arm data and the sensor data. So now we'll focus more on the hardware component. Here's the hardware schematic again. You can see there's 4 different I2C buses that's each connected to a set of optical distance sensors. And for the microcontroller, we decided to use the STM32F7 processor, which is a high-performance chip based on the ARM Cortex-M7. We decided to use the chip because due to our lack of dependency on battery, and since there are external power sources available, and we wanted to have more performance in an effort to help limit the processing time between getting the sensor data to sending it out to our software system through UR. As you can see here, the microcontroller have 4 different I2C buses that can help us separate out the sensor. So we'll talk more about later, but the sensor that we're using are in the breakout board form. So the pull resistors are still attached. The independent I2C buses help us prevent them from closing together, and which will produce a lower pull resistance for each bus that can result in overdrawing current through the devices and overheat. The microcontroller also provides UR communication that is connected to a UR converter, as shown by the bottom right, and to USB, where the USB is connected to a computer that's running our software system to send our sensor data into. Lastly, we use the ST-Link debugger to program the chip.
For the sensors that we chose to use, we chose to use the VL series time-of-flight sensors made by ST Microelectronics. They are Class 1 optical sensors. That means they use infrared light to measure physical distances, thus being safe for the eyes. This is especially important for our purpose because we don't want to damage our patients' eyes during surgery. The measurement latency for these sensors is about 20 milliseconds, and the accuracy distance, the sensors are accurate at distances between 2.5 centimeters to about 80 centimeters. We measured these numbers experimentally. We found that closer than 2.5 centimeters, the sensor readings tended to bottom out, while at about more than 80 centimeters, the measurements were wildly inconsistent. The sensors also have a 25-degree field of view, which looks a bit like a narrow cone. Hence, we need so many sensors, about 30 of them, all over the arm to get a complete coverage of the arm's environment. We communicate with these sensors using I2C, and because we have so many sensors, we chose to use shielded wire to connect the sensors to the PCB to minimize any sort of crosstalk and interference. To mount the sensors on the arm, we designed and 3D printed 3 different types of mounts. These mounts correspond to different parts of the arm and head that the sensors are attached to. We attach these sensors to the arm using mounting putty, specifically because we're in the prototyping phase. This mounting putty is strong enough to adhere the sensors to the arm during motion, but they're also easy enough to take off without residue, so that we can move them around the arm freely. We also use zip ties to attach the shielded wire to the arms so that we can minimize the downward force on the mounts because the wires are very long and heavy. Here we have 2 perspectives of the CAD model of the robotic arm with the microscope head on it and also our PCB. The red dots on the arm signify sensor placements where we chose to put our sensors on the arm. Unfortunately, since we were unable to actually physically test these placements, there might still be blind spots we have not accounted for. This is our PCB that we designed. The picture is our final printed PCB. This PCB is a 4-layer PCB, and it is about 6 inches by 7 inches. This PCB is fairly large with a lot of extra space, but we had to make it this large because of the headers around the edge of the board. Each of these headers is where all the sensors plug into, and in order to actually get to the headers to plug them in, we had to lay them out at the edges of the board, hence the large size. The PCB has two distinct power sources. One primary power source is the USB connection, and it is responsible for powering all the onboard PCB components, such as the STM32 processor. Furthermore, we have a secondary power source from a 5-volt 2-amp wall adapter that plugs into a barrel jack at the top of the PCB. This is responsible for powering all the sensors at the edge of the board, since the USB connection was not enough to supply power for the entire board and the sensors. Furthermore, although we're only using about 30 sensors, there's room for 36 sensors on the PCB in case we needed extra room for sensor expansion.
Here we have our microcontroller software workflow. It's pretty simple. We first have to initialize all the peripherals like UR and I2C. Next, we set up all the sensor devices, do I2C communication to all the sensor to set up the addresses and make sure we're getting all the data correctly. Next, we go into a cycle of reading the sensor data to I2C and transmitting those data to our software system to UR. Each cycle, there's 15 to 25 millisecond delay, depending on the mode of sensor that we're using. But those delays are required since any delay less than that would prevent the distance sensor from collecting the data correctly. Next, we'll focus on the software components.
Yeah, this is an overview of how our software works. So looking in the center, this is object detection. That's the core of our application. What this does is it takes a lot of information, such as sensor distances and the angles and angular velocities of each of the joints, and uses that information to determine if the arm is about to collide with an object and set the arm's mode. So to read some of that information in, if you look at the top left, you can see the sensor data block, which passes information through UART to the serial port communication that then passes sensor distances to object detection. Communicating with the arm is a little more complicated because we have to both send and receive data. Some of the information we send is the operating modes for the arm, and some of the information we receive are the joints and velocities, or yeah, the angles and velocities of each of the joints. We get that information using the RTD connection through the control system. We also use all that information, the sensor distances and angular joint angles and velocities, to visualize the arm and all the sensors. And finally, we have an Android app that we can use to remotely view and control the arm.
Our software is mainly dependent on the universal robotic arm that was provided to us by TrueVision and Alcon. The software uses a real-time data exchange protocol to communicate with the arm to receive the data, such as the joint angle and velocity. And within the arm, it uses the UR script programming language to control its logic. And in times where we don't have the physical arm available, we use the polyscope UR simulator for our development, which provides enough information as the physical arm for development.
Here's a picture showing our visualization. On the right, we have polyscope showing the state of the arm, and on the left, you can see our visualization with the arm in the same position. However, our visualization has some additional information, such as the head of the arm that's drawn. Also looking, you can see a bunch of red lines that are crossing the screen. Each of these lines corresponds to a sensor, pointing in the direction that it's trying to sense data. If the sensor detects an object, you can see a red circle appears, and the red line is drawn shorter to indicate the distance. If the object is detected far away, the circle is going to be large because the cross-section of the detection cone is going to be large. However, if the object is detected very near to the sensor, that circle is going to be small because the cross-section of this cone is smaller. We can also place obstacles in our simulation, such as the slightly transparent cube in kind of the back of the simulation. And looking at the top left, we also have a few control boxes and panels, so we can look at sensor data to make sure we're reading in the correct values. We can also toggle on obstacles, and we can manually set the control mode of the arm. One of the features we use to give more accurate results is sensor enabling, which means we only stop the arm if sensors that are moving forward or moving in the direction of the normal detect an object that's close, and we ignore all other sensors because they're not in danger of running into an obstacle. So in this picture right here, if you look on the right in polyscope, the right arrow is grayed out, which means that the head of the arm is currently moving to the right. If you look on the left, you can see that some of the sensors are red, which means that they're disabled, but some of the sensors are drawn green, which means that they're currently enabled, and if they detect an object that is close, the arm will stop. However, sometimes just using sensor data isn't enough to see if the arm should stop. There are a few scenarios where the sensors get blocked by the arm itself. In that case, we can use the model of the arm directly to determine if the arm is about to run into itself. How we do that is we model each segment of the arm as a rectangular prism, and if any of those rectangular prisms intersect, that means the arm is about to run into itself and it should probably stop. If the arm stops due to rectangular prisms intersecting, we wait until the torque center, we use the torque sensor to determine if any of the rectangular prisms are moving apart from each other before resuming motion safely.
We created an Android app to allow for remote control of the robotic arm and to get feedback from the onboard SafeVision system. The app communicates with the Windows host machine via a TCP client. The Windows host machine has a server created using WinSock. The server, the client, arm joint positions, and sensor data so that the arm can model in the app, so the app can model a OpenGL simulation of the arm in real time. The Android app also allows for control of the arm by giving the user independent control of each of the 6 joints of the arm. In case of conflicting commands between local and remote, local control will always take priority to prevent any sort of mishaps from occurring.
Here are 3 biggest challenges we faced during the development of SafeVision. First, we had to limit sensors to those in the direction of motion. In addition, sensors that detect the arm itself should be ignored. In the top right image, we have an example where the sensor is detecting a part of the arm that it will never collide with. And in the bottom right, we see that the sensor is still useful in other situations. Second, given the speed of the arm and distance range of the sensors, we have roughly half a second to stop the arm. Therefore, we had to optimize hardware and software for speed. Finally, due to COVID-19, we had to work remotely, which forced us to focus on software. We attempted to simulate physical testing with situation tests and increase the use of SafeVision with an Android app. Here is a demo of SafeVision.
The following video is an in-person test of the collision detection system. We have 2 sensors on each side of the head. When they detect a hand, the arm slows to a stop, and when no obstacles are detected, the arm smoothly accelerates and resumes its movement. This next section demonstrates situation tests. Because of COVID-19, we couldn't do any more in-person tests, so we designed virtual tests to check our collision system. Even though these tests are virtual, the interfaces for the Universal Robotics Simulator and the real arm are identical, making it easy to switch between the 2. Each situation test has 3 steps. First, the arm moves to its starting position. Then, obstacles are placed in the simulation, and finally, the arm moves to its end position and may or may not stop. In the test just shown, the arm correctly stopped because a sensor near the head of the arm detected a nearby obstacle. In this next test, the arm starts very close to an obstacle. However, because the arm moves away from the obstacle and isn't in danger of colliding, the arm doesn't stop. This next test demonstrates how the arm stops before colliding with itself. This test doesn't need sensor data because it uses a simulated model of the arm. When the base and head of the arm get too close, the arm stops. Finally, here's a demo of the SafeVision Android app. There are 3 windows on screen. The left window is Polyscope, which is the UR arm simulator. The right window is our visualization program, and the phone shows the app. Before using the app to control the arm, users need to submit the correct IP address, port, and password. This brings the user to the control page. The top shows a visualization of the arm and its sensors. Right under that, there are 3 radio buttons that show the arm's operating mode. And under that, there are 6 sliders controlling the arm's joint angles. When users change joint angles, all 3 visualizations update together, which means that data is being passed correctly, from the app to our visualization through an HTTP server, and then to the arm through a TCP connection. When the user isn't moving a joint, the arm goes into stop mode, which can be seen both in the app and in the visualization. Even when the user controls the arm through the app, collision detection is still enabled, which means the arm stops before colliding with obstacles. This app, with a password-protected login, visualization, and collision detection, enables people to safely view and control the arm from remote locations. The following video.
We'd like to thank everyone who help us with the project. Especially would like to thank Yupei and Patrick from True Vision Outcome, and Professor Yoga, along with our TAs, Kyles and Aditya, for making this project possible. We're open to any questions.
I had a question.
Yeah.
So in a hospital environment, you would probably be covering the microscope with plastic to keep it hermetically sealed. So does the sensor still work in those circumstances?
I don't think we thought about that, to be honest.
Yeah, I don't think we've tested this. It was more of a prototype or a proof of concept to prove whether we could stop the arm, and we would have to adapt, I guess, once it actually went through.
That's a good point, though. Thank you for the question.
I have a question. This is Yupei from Alcom. So if you guys have more time, what else do you guys think you can improve other than testing the hardware on the arm, which did not happen, unfortunately, due to the COVID-19? But other than that, what else do you guys think there's place for improvement?
So right now, with our PCB, there are some errors that we can, well, hardware obviously, like more PCB testing to make it better, because right now there's some bugs with it. But other than that, I think we want to optimize the algorithm for the Android app to the SafeVision program, since the control, as you saw in the demo video, is not very smooth. So we probably want to update that. But other than that, we really need the physical arm to be able to further the development of SafeVision.
We'd also add more features to the app because the app is pretty bare bones right now.
Thank you. You guys did a good job.
Thank you, Yupei.
Thank you.
Thank you.